problem and see if by taking into account some physical coordinatization, something can come up. And in this case, it is first of all just a model, and it will concern, as you may notice maybe already from the title anyway, it will concern dark matter phenomenology, but only galaxy rotation curves, and so therefore just a chunk of what is actually the full scenario of dark matter phenomenology. It's a model, and we also made some assumption because while treating it, we were saying, okay, we are encountering some difficulties more and more, we are losing a bit maybe the key message of what we can get from the model and what we can implement with the dressing, in fact. And so I will show you which are the assumptions that we have made to simplify the treatment of the model, but it's already encouraging to see that somehow is something interesting that we got by applying to some concrete physical system. And so this is how to raise the galaxy rotation curves via dressing, and is now in collaboration with Jordan in a paper that will soon appear, I think, in these days in PRT. So it concerns the context is that of galaxy rotation curves, and so in particular spiral galaxies. And what is done, we may know that usually you measure somehow the orbital speed of stars and galaxies in function of their distance from the galactic center. And here we have two scenarios. One is the theoretical one we produce from GR, from the Newtonian limit of GR, so Newtonian gravity, in which we typically see the curve is famously known as a problem that the curve increases and then decreases with increases distance, and it gives what is called a Keplerian decline. And then on the other hand, what we observe via redshift is that the rotation curves of galaxies typically remain flat and sometimes even increase a bit with, they rise a bit at large gravity. And so this is commonly the reason why we talk about the dark matter, because we say, okay, there is some gravitational effect driven by something that we cannot somehow observe. It does not interact, or it weakly interact. It interacts only gravitationally, and therefore dark matter. And those are some reviews that we have, because of course the literature on dark matter is huge. We were completely new to the field essentially, so we had to the original papers and then to different reviews in different contexts. Some particularly useful because in particular this provides at the very end of the paper a full bibliography divided by topics like dark matter phenomenology regarding galaxy rotation curves, galaxy dynamics, CMB, and so on. So that was useful for this reason, to orientate a bit ourselves in the field. And so in our work, what we did is to produce a manifest invariant formulation via dressing, so as Jordan just showed before. And we have applied in particular the dressing to GR, in which we have to a general-relativistic scenario in which the field in play is metric, plus 4 scalar fields, which are considered to represent the 4 velocity of dust field in the galaxy. And this, as Jordan was already mentioning before, is reminiscent of scalar coordinatization of Brown and Lukács. And in particular, phi provided the dressing field for achieving diffeom-invariance, and it acts as a physical reference system. And we have applied this. I will show you how to galaxy rotation curves. We have taken the true data from a database, and I will show you how. And we've noticed that by taking the dressing theory into account, the result with the dressing is that the model follows pretty much well the galaxy rotation, the observed galaxy rotation curves. And so it reproduces some effect without invoking further field in the theory, just GR and dust, and without having further fields, it reproduces the effects that are traditionally attributed to dark matter. I repeat, it is just a model, it is not the full scenario of dark matter phenomenology, but just a galaxy rotation curves. Yes?
Is this thus following the galaxy in its rotation?
Yeah, it is the content, because from the perspective of the scale of the galaxy, thus is what composes the galaxy. So it's an effective model in which you have star, gas, whatever composes. Yeah, these are two moving frames. Yes, exactly.
But sorry, so this dust describes the ordinary content of your galaxy. It's not in any case associated with
effectively, of course, as a field, and it actually represents for the velocity of the dust. I will show you also, because at a certain point we have, after obtaining the results, we have to just check that it can really reproduce this for velocity of possibly existing dust in composing galaxies. So, yeah. And so the plot will be the first, I will pass through, okay, here I put also a brief recap of the dressing field method. I will just pass through the slides because they were already reviewed by Jordan. And in particular, applying it to GR plus the scalar field. Then we will consider the very short shade metric to provide the baseline geometry, and here is one first assumption. So I'm assuming spherical symmetry with a central mass, and so to simplify a bit the treatment of the model of the galaxy. Okay. And then we will show that the scalar profile allows to have, when we express the rotation velocity, we will have a corrective constant term that will be allowed by the scalar profile by the dressing via the scalar, and therefore it will allow consistency, and we will compare, we will do a phenomenological comparison of the dress model to the observed rotation curve to have this erasing of the galaxy rotation curve.
Sorry, why aren't you considering a Kerr metric instead of a short shape? Since Kerr is rotating.
Yeah, I know.
For simplicity, really. To make life easy.
It's ready to see if we can kind of if we can have some reliable results. So we check also kind of the quality side of the fit of the result. And if we get something that still is encouraging, then maybe we may think of
you can generalize it.
It's a kind of baby step, you know.
Very simple model at this stage, especially after the introduction that Jordan already did. The dressing, you will see that it's just standard things in astrophysics and galaxy rotation dynamics applied to the dress case. And so this is just a picture that, again, Jordan was mentioning to visualize what happens when you dress. We have also all the formal aspects, more abstract and more concrete in this paper. This applied to supersymmetry, this to general-relativistic gauge field theory, this to unconventional supersymmetry, in particular showing that the matter ansatz can be seen as a dressing. And in this paper, a bit a review of those in which we also have these more intuitive pictures, and we have also implemented the BRST dress, the BRST formalism dress version, also to show really the difference between gauge fields and dressing. And so essentially what we have, as we were saying before, for this is field space seen as a bundle. When you gauge fix, you fix a slice with some gauge fixing constraints in the bundle, while the dressing operation implements the projection on the moduli space. It is what it does operationally. So, and this is what Jordan already showed. So how, at the kinematical level, how we extract a dressing field for diffeomorphism, and this will be what we will do with, this will be the scalar field in the application that I'm going to show you. And how once we extract it with the physical, written in terms of the field content that we have at our disposal, we also achieve a relational interpretation. It is written in this way, and we write the dress field that are invariant under diffeomorphism. Here we are just interested in diffeomorphism-invariance. They are not object, the dress fields are not object on the mainly for the bottom dress regions, and also in these works we have discussed this notion. And anyway, it's interesting already by itself, also conceptually and also quite technically. It's not that difficult, but conceptually the notion of dress region is something that personally I find interesting. And at the dynamical level, it happens what we were mentioning before. So we just address the Lagrangian, it will be strictly diffeomorphism-invariant, And the field equation, in fact, they will have the same functional expression as the bare one. That is also why the theory is able to capture some physics, even though it's bare maybe in principle. So, but the dressed one is what should actually be compared with experiments. And you really notice what's the difference only if you unfold the dressing in the dressed theory. So what we will consider now is therefore this field content with the metric and the scalar fields. So matter is described as this dust supplying scalar fields for scalar fields. We write their transformation under diffeomorphisms. We are pulled back in composition. And we can take the dressing field to be written in terms of the scalar field, in particular in terms of the inverse mapping this way. And in fact, if we check how it transforms under diffeomorphisms, it transforms as a dressing field for diffeomorphism should. And we receive what is the dressed metric, but then we have also the self-dressing of the scalar field, of course, and it will just yield the identity in the dressed regions, which means this can be interpreted as saying that the scalar field is in its own reference frame, is sitting on its own reference frame. So this is the dressed metric, just in components. So here I decided to put in indices. This is the Jacobian of the dressing, of the physical coordinatization. Same formulas that Jordan showed before, just here I'm calling the Jacobian J and not G, because G will be the cosmological the Newton constant, the gravitational constant, so. And then what we have to do in this case is to do perturbation theory, and therefore to consider an infinitesimal dressing. So this is what is useful to study in an effective way these models. So we write the dressed coordinates that we define as being the scalar field components in this way, with the first contribution written in terms of x mu of the bare coordinates, plus a small deformation, and this is key and is chi and is key because it will appear all along the model that I'm now going to show you. So it's just a small deformation that in the end one may rewrite in terms of the bare components, and you can imagine it as telling you how much the physical coordinatization is contributing to the description of the model. So this is, once we have these dressed coordinates, we replace in this expression, we get the dressed metric, where GB is the bare metric in components. And so now we are going to apply this, so consider as bare metric the Schwarzschild metric, simplest case, spherical symmetry. And also we focus on the equatorial plane, so we fix the theta to pi half, because anyway that's what you look at when you look at galaxies, spiral galaxies in the rotational curves. So we simplify the framework. This is the expression F is the usual factor in terms of M and there are. Those are the metric component. And now we dress them, so we take this expression and we plug them back into the formula for the dress metric. And we get here I wrote only the relevant dress components that are useful then for the rest of the analysis. And we have also assumed some compatibility constraints that are those that are compatible with this cosmological astrophysical setup, just again to simplify the things. Because when you dress the metric, it is not automatically Schwarzschild again, just in dress forms. You will also get out of diagonal components. And so the things become harder and harder, but at least in this case, to treat them in a straightforward way and compare with experiments with observations, that's what was.
Yes. These four scalar fields are minimally coupled to Einstein, or they are like proof scalars on the top of Schwarzschild geometry?
Yes, okay, we did start directly from not even just taking the metric and thinking that the scalar field is contributing to what is described within the Schwarzschild geometry. So it's just what composes the galaxy somehow. We don't even look, in principle you may do that, yes, in fact, that is actually interesting to see the dressing under that perspective. Yeah. And so what we get is this. This is the dress theory, the dress metric, the components that are relevant to the analysis of the rotational curves. And we are going to compare these with observation. We will see how. So we first notice that these were the dressed components, but still written in terms of the bare one, because when we do perturbation theory, we replace, and then we have like in the formula that I showed you before, you just have an expression for this object. Then what you have to compare with observation, according with this paradigm, is the dressed theory. Therefore, we just substitute, we invert the formula, we just substitute everything to have it in terms of dressed objects and this small deformation.
Sorry, how do you define R bar? Is it the distance
Yeah,
from...
it is, I will show you, it is
The
the
distance from
R
the horizon.
plus chi R. Yeah, exactly. It is this. Here, this holds for all components. So we have R bar, it's R plus chi R. Yes, exactly. It's the dressed R. It's the physical R. Not the bare, it's just like in the bare manifold, as we were saying before, the mathematical description decouples from the model. You don't have to consider anymore once you have just the theory. So these are just the... Yeah.
But then R bar minus chi R means the bare one.
Yeah, exactly, but you write everything functionally in terms of R bar to keep control of what's changing. You can also just... here the key point was to unfold it to see what's the difference, and in fact the difference we will see it in a while what happens by doing this. So we also take, these are the derivative that comes at play in the next slide when you have to derive the rotational velocity of the galaxies. Just those are the relevant objects, say, and of course then you can calculate other components and their derivative in principle. And so what we now do, this is standard to galaxy rotation curves. So this is what they typically do when they want to obtain the velocity, the rotational velocity, and then compare with observation. The only difference is that here everything is dressed. So we take a test particle, we write its Lagrangian. In terms of it will be the dressed Lagrangian with the dressed metric, and these are the dressed for velocities. We get the dressed energy and dressed angular momentum in this way, as usual. And then here we did a further assumption that was to consider circular orbits, and therefore to set, this is also what they formally do, so we follow it. There is some simplification we can do with it. So circular orbits, and so we have this equation related the energy and the effective potential that now is dressed and expressed in terms of the dress coordinates. And then, since by exploiting also this formula, we replace this inside this equation, we get the phi dot bar and t dot bar, that are the expression for the dot derivative of the phi component dressed, and the same for t. Then we focus on a physical case, or on a time-like case, and so we have this constraint. We replace this expression into this, and by solving and knowing what how E is related to V, we get the expression for the effective potential. And also we require stability of the configuration, so that we implement this condition which yields the angular momentum. And so these are, everything is just a standard but dressed. And then what we do is writing the rotational velocity, which is written in terms of phi dot dressed in terms of L and G phi phi, and so we replace, we get the formula for the rotational velocity. And now, this is important, we also set ourselves in the weak field limit. This is another assumption that is typically done when one studies galaxy rotation curves in uneffective models, and we get this result. So we go in here there is also another point that I didn't mention before, but it's the fact that since chi is a small perturbation, whenever there are second or higher order terms, we neglect them. So these and in the weak field limit we get these results in which we say that first we have this contribution, which is the usual Keplerian term, say, plus another contribution. And so, which depends on the dressed coordinates and on chi r, so on the small perturbation. And so we notice that for chi r equal to k r squared, so written in this way in terms of r squared, so it goes like this, with k constant greater than 0, we have a constant contribution that deforms the Keplerian result.
Where do you get this chi r? How do you get this chi r?
Chi r is chi, if you have, because it's in the other slide, it's r bar, is r plus chi r, and so we just invert it is r bar, chi r is r bar minus r, and so this is something. This is what we get for chi as a function of r bar, and this is an assumption that we are making at this moment. We're saying if it has this behavior, we get this result. So, but till now we don't have a constraint on the field, so we say, let's see if constraining it in such a way to cure the Keplerian contribution in a constant with a constant term, it can still reproduce what a scalar profile, which has to have scalar density, the right scalar density and mass, and it shall be able to describe the forward velocity exactly. And actually, in fact, if you plug the dressed expression into the Schwarzschild components of the metric, you see that there is an effective mass, and for instance here also you have some deformation I can show you after the slides that are induced by chi, the deformation. So say, okay, I have some constraint if I want this effective mass, which is not the physical one, it's an effective mass to be measured in 0. So there are constraints that you can give to chi. Some are just assumption, simplification that have to be consistent with what you want to describe. Some other, like this one, of course, are stronger because this is telling you, okay, if this is the behavior of chi, this is what we get a constant corrective term.
Yeah, but you could have a different chi for some other reason, like a chi could be cubic in r power.
We didn't analyze what happens in that case. But yeah, in principle, if it is consistent, if it is consistent with the fact that it has somehow we expected the small coordinatization to increase while you go far from in distance, and so this is the case for this object, so, and not to decrease, for instance, because you would expect that if you move far from the reference in which you are set, you contribute more to a physical coordinatization. So. But yes, in principle, sure, you may also reproduce other effects. Sure.
So, I'm quite confused with the bar, non-bar, but the fact that we are considering R greater than 2mg, is this consistent with the perturbative regime?
Yes, it is the weak field limit, but the perturbative regime that we are considering is chi that is affected, is chi that is.
Okay, so it's not too large, bar is not too large, but it's greater than
exactly.
2mg.
Yeah, of course, the galaxy is galaxy. And so the point is that kappa also has to be a constant measured at 0, but it has, I didn't write it here, but it has to be also a small constant. That is what we know, of course, to contain C.
I have a question is related to the interpretation of the dressing, the physical interpretation of the dressing. Am I understanding well that dressing a field, another field, not the dressing field, somehow means to observe the field in the framework of the dressing field?
Yes, exactly.
Right? So it's like a choice of framework, and by definition, once you choose a framework, everything is invariant somehow, right?
Yeah.
I don't know why.
In some models, it is more evident this kind of interpretation. For instance, in the seminar that Jordan did some months ago, I think, on the
I remember this interpretation of quantum mechanics.
Exactly.
Yeah.
Relativistic quantum mechanics. what you have is that you can take as a dressing field, a dressing object, each one of the particles, so you have this ability also in the choice of dressing that reflects the residual symmetry of the second kind. They change and they exhibit somehow they reflect reference frame covariance.
Yes.
So in that case, it's more evident.
So if you fix, I was wondering if this dressing by means of this dust means or can be interpreted as the fact that you are observing the galaxy in the framework of the dust.
That is describing with a physical coordinate system.
Yes,
So in principle, well, whatever it actually means concretely, yes, you may interpret it with a physical reference system that in fact self-addressed is resting in its frame. So it's not
So self-addressed is
it's like saying somehow that in the bare description you may have some coordinate artifact, some bare coordinate, so non-physical coordinate artifact, while in the dressed version you are coordinatizing with physical system and you get something more. The idea should be something like that.
By referring to some intrinsic frame, somehow you make everything invariant.
Because
And so I think that kind of setup, I guess, would be the best. Would be cosmological. Cosmology would be the best setup to that kind of stuff. Typically, cosmological and perturbation theory, in which you can really, on those scale, matter is just dust, pressureless dust, and it's clear that therefore, and typically in cosmology, as you said, you see, we are. You look at everything from a co-moving perspective. So you are really you sit within the dust and everything.
So you kind of following the dust its motion.
Cosmological
in that
perturbation
case,
theory is even more evident also as an interpretation possible. In fact, it's something that we want to look at.
But for this, just to remind that the point is to have a simple model and to it is baby step, first attempt, and so for example for that assumption there, the point was to say, okay, how far can we go with such a simple assumption so that we get a simple constant correction and trivial, and then but the heavy lift work was after what Lucrezia has been leading on is to read the data. How good can you, with such a simple assumption, how good can you fit a bunch of data? That was just a test to see how it goes, and it is encouraging, I would say, for now. Because of course there's many sophistication to be needed as
many improvements, releasing some assumptions. But not only in the model, also in the data, as we will see now. I will show you which are the difficulties that you encounter when you really want to compare with somehow with observation or with data. So,
this probably allows you to find an estimation or estimate for the value of k.
Yeah, exactly.
Does that fit most of the galaxies or just one particular galaxy? Because it might be different from
that is where we want to arrive. And it is different for different galaxies, thinking of having a different distribution of matter, not homogeneous from galaxy to galaxy, but it is of the same order of magnitude changes of activity. So the important thing is that we wanted to check at least, it's again a simple model, but it's encouraging to see that it will be, I will show you, a single fit parameter. So we want a single parameter fit, you see
because it might be related to a different type of galaxies. Galaxies that are growing,
exactly. It fits well with a similar k parameter. Similar, I mean small, same order of magnitude. They just change a bit the number, really. Also, those galaxies that are a bit stranger in the theory. Usually, when we imagine the galaxy rotation theory, we imagine something that goes like this. And there are some that are more peculiar. They are typical, anyway, spiral galaxies that are observed under that perspective, and also because of creating, in fact, the galaxy rotation curves. And it fits well and with this characteristic of K, also those kind of galaxies. There are other galaxies that see the fit is good, but they have like 4 data in the data set, and so you cannot even read that. So it depends on the model. Yes, okay, this is the assumption of the model, and we check for consistency of it. We have to see what happens to K, but the other part also comes from the data set, from having a good data set. Yeah. So this is what I was mentioning before, that one check that anyway one has to do is to see if you can really interpret the dress for velocity as the dress for velocity of the moving dust field. So this is the expression that by definition what we expected. And in fact we can then again unfold in terms of the VR1. The VR1 we know that it can be written in this way. Tau is the Fourier time, this is the normalization condition taken for the velocities, and so we unfold the dressing in this way, and using our physical coordinatization, again unfolding it, we get this result. And now we check that the constraint that we have, at least the relevant ones at this stage on chi, and by using the barometry, they give us something that can be interpreted as a velocity. So the relevant conditions that we have on chi that are either consistently assumed, as I showed you before for simplicity, or they are obtained. For instance, this one is actually obtained, if you want I can show you this after, but just the fact is that you have an effective mass, you may want it to be positive in principle, and so for this to be the case, dt chi t has to be a small constant. So this is one. The other just follow from what I showed you before. And so you can prove that this is in fact interpretable as the dress for velocity of a dust field. We expect a form of this kind in particular. And if we plug this constraint into this equation for the chi dx in particular, we get this result, and so this, and we may see that yes, it is not 1, 0, 0, 0, but there is a small deformation parameter in the dress for velocity, and you can also explicitly prove, going again in the weak field limit, which is the assumption in this model, that it is also normalized to -1. So this just for completeness, and now we can move to the interesting part, that is that we may now want to fit the dressing field derived rotation curves with those of observed rotation curves of spiral galaxies. And so we have taken, in principle, we started from 2 galaxies from this database, which is Spitzer Photometry and RC stands for rotation curves. So this is the paper in which they mentioned we created this database. And so we have chosen those 2 from the new general catalog, those 2 because they have a high quality rotation curves, meaning that the error bars are not super disproportionate with respect to the data. And also we have a pretty much high number of data points, which is important also to have a good. And so we have extracted from the SPARC dataset the rotational velocity of the components of the galaxy. They have one that is the full velocity, and then some other that are extracted, and they are actually obtained, they are calculated from the surface brightness of the stars. So we have gas, disk, and bulge components. And then we have used those data to estimate the corresponding baryonic mass contribution, only baryonic, because at this stage we think, we have in mind that we don't need the further mass but the baryonic one present in the galaxy to try to describe, to fit the galaxy rotation curves. And we have also rescaled, we have noticed that this is commonly done because those masses are obtained with light factors only, so from surface brightness, say. So you have to rescale them to take into account mass to light corrective factors, and we have taken them from the literature. And we have thus obtained the total baryonic mass of the galaxies. And so we have, this is just the square root of the velocity that I showed you before. So we have compared this with observation, with G in cosmological units, and where we remind that in fact V naught dress is a function of K. k. So we did 1 parameter fit for k. And so those are just what we have plotted, taking the data from the data set. This is for this spiral galaxy, this is for another one. You see that here something happens here, error bars appear, so anyway, data are affected by this kind of thing. And one has 43 data points, in the other 73. We found some, there are 175 galaxies in the catalog, in this SPARC catalog. Some have even more data, and so we have decided then to also analyze all of them in the end. Some other have 10, 15, and so it becomes harder to trace so those are the mass profile that we have obtained for the two galaxies. So we have taken the various components, we have summed them, but we have also adopted this corrective factor mass to light for gas, disk, and bulge obtained again from the literature. Those are just to show you that we did obtain the total baryonic mass, but those plots are not relevant in the following. And those are the crucial ones, in which we have, for the two galaxies, we have plotted the observed rotation curves, that are the black ones. These gray ones are the baryonic Baire model, the baryonic Baire curves that one would obtain using the same baryonic mass, but for a purely Keplerian behavior. And this red one is what we obtain via dressing. And so it is 1 parameter fit. It is the results you can see. This is what I was mentioning before, that they have the same order of magnitude, precision 10 to the minus 5, but they change a bit. They are slightly different numbers, that for sure. And then we did also analyze the quality, say, of the statistical fit by using the R squared that takes into account the residual of the theory. And this is, well, say that it's more reliable, even though it checks other aspects of the fit, than the chi-squared in the case in which you don't have access, either if you don't have a really high quality data concerning the error bars, and also in the case in which you cannot propagate, the error was not propagated in the SPARC dataset for velocity of the gas, light, bulge, and disk, and so we couldn't have the error bars to redo a chi-squared test. And so we did an R square, and this tells you if it is 1, it is a perfect fit. If it is 0, it means that your model does not represent what you're comparing with, and so this is pretty much a good fit. And those are also the residuals, so this is the plot of the difference between the values of the observed velocity and those of the dressing. And we decided to compare those of the obtained via the dressing and those of the baryonic models, also to show how much they will be fair. Of course, we have some fluctuation here and here, but you see that more or less it is close to 0. That is important for the receiver to see that there is not much difference. And then, well, also because the referee asked us, but we were also curious actually to see. And so we decided to plot all the galaxies of the catalog. We have obtained, there are no anomalies in the results that we have obtained. It's just that those galaxies that have less data are more difficult to treat in general. And there are some that have curves of this kind, as we were mentioning before, that is typically they do like this, you see? But this, for instance, the black one is the observed, so. And again, you can see, but okay, here the numbers are a bit small, but but you can see that the kappa k is always smaller and same order of magnitude. It's just changing as a number, and R squared is always close to 1. And we have galaxies either with 30, 24, 34, 44, 21, 46 data points. So more than 20 to do an analysis. This is what we've noticed in the end. Yeah.
So if k is equal to 0, you recover the curve that is the lower one, or not?
Yeah.
If k
With Keplerian.
yes,
Okay.
it's a smaller.
It would mean no coordinatization whatsoever.
Yes. And so here are other examples. So some that have this kind of curve anyway, the geography, and you see anyway the important thing was for us to see how much it is different in fact from the Keplerian, also how much it can fit, and if it can fit in consistent ways the galaxy. And so in summary, we have seen that with the Dresden method, with our relational physical coordinatization in a diffeom-invariant framework, we have that rotational velocity can be cured, if we want to, they comprise constant corrective terms, and therefore this flattens the galaxy rotation curves, mirroring the effects in dark only attributed to dark matter. We are using Scalar, so the dust field, as a physical reference frame, and it is subject to conditions that are compatible with the fact that we expect it to be the four velocity of this dust field. And the interesting point is that despite the simplicity of the model and our way, the data that we have at our disposal, it is a good fit with only one parameter, so it's kind of encouraging. And the part of the future work in this respect will be, here we focus on rotation curves, but as I was mentioning before, dark matter phenomenology also is more involved, and we have also to treat maybe aspects as the CMB and the anisotropes and so on, so maybe this could be a possible thing to explore next. And also, since the Dresden method is extremely versatile, we were thinking of implementing the diffeom dressing to get a diffeomorphism-invariant version of cosmological perturbation theory, large-scale structure formation, and so on. And also study other possible astrophysical, cosmological, either effects, maybe changing some variables at play, but also some other objects via the dressing. So that's it. Thank you for having me.